Hey everybody, it's Mr. Zabo coming at you with section 9.3 notes. We're bringing back a couple old friends, starting with an altitude. Remember, an altitude is a segment that is drawn from the vertex of a triangle perpendicular to the opposite side. In this case, we're going to be drawing altitudes inside right triangles, specifically to the hypotenuse of a right triangle. So in Theorem 68, we have the big triangle ACB, where angle C is the right angle, and we're going to draw segment CD, which is the altitude, from the right angle C to the hypotenuse side AB. In doing so, we have created three similar triangles. Those are triangles ADC, triangle CDB, and triangle ACB. And we can see trying to reorganize those triangles can be a little bit tricky into what triangle is what. But if I think about my right angle in my large triangle has C as the angle, and then try to look at the triangle that I have in my dashed line with red, the right angle is at vertex D, so I have to name these triangles accurately. And in my blue triangle that I've outlined up there, the right angle is also point D. And then we think about what looks to be like the smaller angle of the other two angles. In my large triangle, from C to get to my smaller angle, looks like it's C to B. So B would go here. In my red triangle, in fact, the smaller angle is likely C. So C would go up here, and then this is B again, giving me these as my final triangles there. And if I were to name each of these triangles something and try to match the names, let's say I called this triangle CAB, then my red triangle would be triangle DAC, and my blue triangle would be triangle DCB. And all three of these triangles are similar by angle-angle similarity. Now, if I take a look at my first two triangle similarities, or my two triangles and the similarity statement, from there I can state that segment AB over segment AC is equal to segment AC over segment AD, using my proportional sides in similar triangles. Similarly, using my second two triangles, I can state that AD over CD is equal to CD over BD, and using the first and third triangles, I can state that AB over CB is equal to CB over DB. In each of these three cases, I want you to recognize that what we've created are geometric means. And AB and AD in my first ratio are my extremes, and AC and AC, those are my means. And I have CD and CD as my means, CB and CB as those means. So we can use these setups when we have an altitude drawn to the hypotenuse of a right triangle, three similar right triangles. So in other words, the altitude to the hypotenuse is the mean proportional to the legs, is another way we can state that. Or we can summarize it using sort of the geometric mean idea. I like to call this the geometric mean mountain. So what I'm talking about is this. If h represents the length of the altitude, h squared, which in our other previous case, that was C and this was D, is CD squared, like in the middle here. H squared is going to be equal to AD times BD. Well, AD is X, and BD is Y. h squared is equal to the proportional sides of those legs. That's one important statement or setup for an equation that we can use. Similarly, I can take the leg of my large triangle, in this case that's B, or it's segment AC. It's this segment here. AC squared, or in this case B squared, is going to be equal to AB. AB is this whole side here. The whole side is C, which is x plus y. So I will just say it's C for now, times AD. In that case, that's x. So I'll also like to look at this as B squared is equal to x times x plus y, because C is x plus y. I show that sometimes by doing this. I have a mountain here where the peak is squared and it's equal to the product of these two pieces. And in the middle I have my mountain. I have my peak h is squared and it's equal to the product of the two bases. And then we can go along the other side and use the same theory here. A squared is going to be equal to y times c in this case, or y times x plus y. And that makes sense because A is segment CB, here's CB squared. AB is C, and DB is y. A squared is equal to y times x plus y. Now let's take that theory and let's actually apply it to a couple of practice problems before you try your own. So if I'm looking at, let's say, number 1 to start, and I'm going to just kind of pick each piece here. I like to start with the altitude. That in this case is y. Y squared is going to be equal to the product of those two bases. In this case, 3 times 5. I'm going to use what we've talked about yesterday with our radicals to simplify this if I can. Y squared is equal to 15, square root both sides, and y is equal technically to plus or minus the square root of 15, but, oh, that's ugly. But y is a side length, so we have to reject the negative option and state simply that y is equal to the positive square root of 15. That's the value for y. Now I'm going to go to the legs of the larger triangle. First, I'll do this one. Z. Z, the base is 3, so I'm going to have z squared equals 3 times. The other side is when I'm going to add the entire length of the hypotenuse. That's 3 plus 5, or 8. So it's 3 times 8. Z squared is equal to 24 when I square root both sides. Yes, I get plus or minus the square root of 24. I reject the negative, and I reduce the radical. Z is going to be equal to square root of 24 is the same as the square root of 4 times 6, so it's 2 square roots of 6. And then last but not least, I can perform the same sort of operation on my x. My x squared is going to be equal to my 5 times the other side here is going to be the entire length of the hypotenuse again, and that is 8. So my x squared is equal to 40. My x is equal to positive or negative square root 40. I'm going to reject the negative. That's the same as square root of 4 times 10, or my x being equal to 2 square roots of 10. I've been able to solve for all 3 variables. For number 2, they're only asking that we find or solve for x and y. I want you guys to hit pause and try that one on your own right now, please. All right, so the last type I want to show you is one where we're actually solving for a part of the original hypotenuse, or the hypotenuse of the longest triangle, the largest triangle. In this case, we see that x is a part of the big triangle's hypotenuse. So we actually have to add x plus 1, the two parts of the large hypotenuse. Then we can set up three separate equations using our mean proportionals. 3, the leg of the large triangle, is the mean proportional, so 3 squared will be equal to 1, the part, times x plus 1. My next equation, using the altitude, y squared is the mean proportion of the two parts or legs of my other triangles, in this case 1 times x, and z is the mean proportional, so z squared is going to be equal to x times x plus 1. I have my three separate equations I can set up, and in fact the only one I can solve right now is the red one. I have to solve that one first because it's the only one that has one variable. So I can go through and solve this and say that 9 is equal to x plus 1, subtract my 1, and get my x value to be equal to 8. Once I know that, I can use substitution. I know that my y squared is going to be equal to 1 times, well, 8. So my y squared is going to be equal to 8. My y is going to be equal to the square root of 8, plus or minus, ignore the or reject the negative, which is going to reduce to 2 square roots of 2. And lastly, I can substitute, not that one, but I can take my 8 here and substitute that into my z squared equation as well. My 8 times 8 plus 1, or my z squared equaling 8 times 9, which is 72. My z will be equal to the square root of 72, which can reduce to, that's 36 times 2 inside my radical, 6 square roots of 2. I want you to take the rest of class to try to finish up the additional problems on this page, numbers 3, 5, 6, and 7. I will have the answer key posted on our calendar. You guys can work in small groups on this. And if you finish, go ahead and work on the homework assignment for sections 9.1 and 9.3.